Hello students, today's agenda is to check your homework and we're going to change from recursive formula to explicit and from explicit to recursive, and you will be able to do 7.7. Excuse me. Today students will be able to change a recursive formula to an explicit and from explicit to recursive. But before you can do that, I want to make sure that you understand the difference between the recursive and the explicit formula. So let's do a small chart. And I'm going to ask you, when do we use the recursive formula? And when do we use the explicit formula? Okay, so recursive is to find only a couple of terms in a sequence, and the explicit is to go directly to a term that is far away from the first few terms. Okay, so let's put that. When we are trying to find only a few terms in a sequence. And I would say that maybe even less than 6 terms, or maybe we can even go up to 8 terms. However, we don't want to do or use the recursive formula if we're going to have like 20 or 30 or even 100 or less if we're doing to the thousands. The explicit formula, when you are trying to find a number or a term that is far away from the first few couple, okay, find a term that is far away. For example, if we're talking about the rabbits like before, like how many rabbits will be there after 1,200 years, or how many rabbits will there be after even 100 years. That's far away, right? So we can say that this is short term and this is long term. Okay, now let's talk about the structure. How does it look for each one? And I'm going to show you one for arithmetic and one for geometric sequence in the recursive and the explicit form. Okay, so for the recursive, we always have f of 1 and f of n equals f of n minus 1. And the initial point, it's f of 1. This is the initial point. So let's write maybe 5 in here. And let's say that for the pattern, we're going to be adding 2. Okay, so this is my initial point. And it goes with my f of 1. This is my pattern. Because it's addition, we call it common difference. So, okay. And so that's how an arithmetic sequence would look in the recursive formula. Okay. Now, what about for the explicit? The explicit only has one part. So it will be always f of n equals, and this includes the initial and the pattern. The initial point right next to the pattern. And since we're adding, you have seen in the previous lessons that you are putting n minus 1 as a factor. So this means exactly the same, but this is to help you find long terms from now, and this is if you want to do a sequence for the next couple of days. Okay, initial point, the pattern. This one has f of n minus 1. This one doesn't have f. Okay, this means look at the previous one. Look at the previous one, and that's why we're dependent on the previous term to be able to find each term in the sequence. Now this is called arithmetic, and the reason is because we're adding. Remember that when we're adding or subtracting, they're called arithmetic sequences. When the pattern is adding or subtracting, it's called arithmetic sequence. Okay, so both of these are arithmetic, but one is recursive, one is explicit. The recursive has always f of 1 and f after the equal sign. The explicit doesn't have f of 1 and it doesn't have f. Okay, and this one is to find a specific term directly. This one you have to find the previous one. Okay, so what about a geometric? How would it look? Again, for the recursive, it's always going to be f of 1, f of n equals f of n minus 1. And geometric, it just means that you're multiplying. You can multiply by a fraction, which is similar to division, or you can multiply by a whole number. So the initial point, let's say, I eat 3 cookies. I've eaten 3 cookies, and I'm gonna double that. Oh, that will be too much. Maybe there are 3 bacteria, and then it doubles every hour. So double means multiply times 2. This is the initial point. And this is the pattern. The pattern for multiplication is called also common ratio. Okay, and again, notice that for the recursive you have f of 1, and then you have f of n equals f of n minus 1 times 2. Now I wanted to say that there are 2 different ways to write this, because sometimes actually the more proper way to write it is to put the 2 as a coefficient. Okay, so let me write it in here. It's exactly the same as this second part. Okay, so it's going to be f of n equals 2 f of n minus 1. Notice how I just brought the 2 over to put it to the left of f of n minus 1. It's the same thing. And I'm showing it to you because you might encounter it like that more often than not. Okay. For the explicit, the geometric formula again has only one equation, and so it's going to be f of n equals, again, initial point and pattern. So the initial point is 3. The pattern is to multiply by 2. And remember that n minus 1, when it's multiplication, you put it as an exponent, okay? N minus 1. So these 2 are exactly the same. Notice how I put the initial point. This one is on top with the first equation. In here, it's right after the equal sign. The pattern goes right next to the initial point. In here, it goes on the second equation. And then n minus 1 is always with the f in here. In here, because it's multiplication, you put it as an exponent. When it's addition, you put it as a factor. Okay, n minus 1 is a factor in here. In here, n minus 1, because it's a geometric, meaning multiplication, it's an exponent or a power. Same thing. Power means exponent. Okay, so this is an arithmetic sequence. This is geometric sequence. And I didn't leave myself some space, so geometric sequence. Arithmetic because you're adding, and geometric because you're multiplying. Okay, and arithmetic is also for subtraction. Okay, so now let's get to our goal, which is to change our recursive formula to an explicit and from an explicit to a recursive. So let me see. If I have this recursive formula, how would you write it as an explicit formula? Well, remember that the explicit only has one part, and you can go back to the chart that we did right now, but it's just f of n equals, remember that in the explicit we only have one equation with both parts, the initial point and the pattern together. So the initial point, the pattern which is plus 5, and because it's addition, my n minus 1 will be a factor. Okay, initial point, pattern, n minus 1. That's all you have to write. Okay, let's do another one. How about this one? You might want to try it and see how you do with that. Okay, so again, I'm sorry, you have your initial point, which is 4, and 3 is the pattern. But notice that the 3 is being multiplied. It's as a coefficient. So again, for my explicit, you always have only one equation, which is f of n all the time. All the time you will have the initial point with the pattern, but in here we don't have plus, so if it's not addition, it's multiplication. And for multiplication, my n minus 1 will always be an exponent. Okay, so that's how you would write f of n equals 4 times 3 to the n minus 1. Okay, as a power, because this is multiplication. Okay, one more. Let me put it in here. I kind of wrote on this one, so please ignore ignore that circle in there. Convert to recursive formula from the explicit. So now it's the other way around. So in this case, notice that for the previous one, in order to know which one is the initial point and the pattern, you have to have n minus 1. But in here, we don't have n minus 1. We only have n, and that's why I circled that. So we can't immediately figure out what the initial point is in here. So guess what we're going to have to do? We're going to have to find f of 1, meaning that that's going to give us our initial point. So we were basically replacing n with 1. So f of 1 is equals to 3 plus 4 times 1. So it's 3 plus 4 times 1 is 4. And that's equals to 7. So f of 1 is my initial point because it's the first term in this explicit formula. Again, we cannot find immediately. Some people would say, oh, the initial point is 3. Only if it was with n minus 1 in here, but it's not. That's why we have to do the list. So f of 2 is 3 plus 4 times 2, which is 3, plus 4 times 2 is 8, and 3 plus 8 is 11. That's my second term. And then I'm going to do f of 3 just to see what the pattern is, okay? This is going to help me figure out the pattern so I can write the recursive formula. So f of 3 is 3 plus 4 times 3, which is 3 plus 4 times 3 is 12, which gives me 15. So now I see, what did I do to get from 7 to 11? It looks like I'm adding 4. Is the same for 11 to 15? Yes. So that means that my pattern is going to be adding 4. And my initial point is 7. So now I can write my recursive formula, and I can even write the explicit if I want to, because right here I have it, but without, I mean after it was simplified. So the recursive, remember that you always have f of 1 equals the initial point, and f of n equals f of n minus 1 with the pattern, so plus 4. Okay, so they gave me the explicit formula, but it's in simplified form, and I had to convert it to recursive formula. Recursive, remember, it has two different parts. F of 1 with the initial point, f of n with the, look at the previous one, plus the pattern. Now, what do I have folded in here? Well, it's actually the explicit formula without being simplified. And how did I get it? I can't get it until I do the 3 terms. Why? Because for the explicit formula without being simplified, I have f of n, initial point, plus pattern, and since it's addition, times n minus 1. If I do distributive property, f times n, I mean 4 times n is 4n, 4 times negative 1 is negative 4, bring down the 7, combine these two terms, and so I get 4n plus 3. I get 7 minus 4 is 3. Notice that this is exactly like this, simplified already. Well, kind of exactly. It's the same as 4n plus 3 is the same as 3 plus 4n. So if they give me the function simplified, I can do this, and from here I can get the explicit formula not simplified or the recursive formula. Okay, but in here they're asking me to do the recursive. Okay, let's try another one. What about this one? Okay, do you want to try it? Pause the video so that you can try and see if you can get it. Remember that the recursive formula has 2 parts to it. And what do you start with? Okay, hopefully you paused it and already have it. Remember that you always have f of 1 equals, f of n equals, f of n minus 1. That it's always part of the recursive formula. F of 1 is your initial point. How come in here I'm able to see the initial and the pattern? If I have n minus 1, that means that this is my initial point, and whatever is next to the n minus 1 is my pattern. Okay, so f of 1 equals 5, and because 5 is next to n minus 1, that's my pattern, and my pattern is to add 5. Whoops. And that's not the initial point. 3 is the initial point. Sorry about that. Did you catch it before I said it? Okay. Hopefully you did. Okay, so that's it. All you're doing is writing it in recursive formula. Okay, let me give you another one. Now I have convert to recursive. And you have f of n equals 4 times 3 to the n minus 1. Because I have n minus 1, that means that I have my initial point and my pattern. Okay, so this is my initial point. The pattern is always next to the n minus 1. So remember f of 1 goes with the initial point, which is 4. And for the pattern, what we will be doing is multiplying by 3. So it's f of n minus 1 times 3. Okay? Now remember that sometimes this will be a coefficient and it's exactly the same thing. Let me write it in here. This can also be written as f of n equals 3 f of n minus 1. 3 f of n minus 1. I squished it too much, oops. Okay, 3 f of n minus 1. So it's exactly the same thing. Okay, just times 3 in here or times 3 in here. Okay, so I think I'm going to give you one last one. Maybe you want to pause it and that way you can practice it on your own. Okay, again, you need f of 1, f of n. And this one will always have f of n minus 1. And the pattern will always be with the n minus 1. So you're multiplying by 7. Again, because it's multiplication, you can put it as a coefficient. I'm not going to do it for this one, but it can be here or here. And your initial point is 4. Okay, so that's it for today. I hope you had fun and enjoy doing 7.7.